Well, hello friends. Welcome back to the program. Today we are going to work on text and fonts and things of that nature because yesterday I posted this screenshot on Twitter of how Ladybird now honors the system color theme on Linux. So text selection uses whatever native selection color you have on Linux, and I was pretty happy with that. But in the comments, Rasmus showed up and pointed out the WE kerning is not looking super good, and he is right about that. It is pretty nasty, and Rasmus is the author of the typeface I'm using, Enter, so he has every right to complain that we are not doing it justice. And I thought today we would try to do him justice and do Enter justice by fixing this issue and implementing whatever is missing to get those W and E glyphs there to snuggle up next to each other. So that's the mission today. And let me see that we have a build. Yes. So we need to have a little test, and I thought we could just make a simple HTML file that just says, well, so we'll just do this, enter, and we'll make it 100 px because why not? And we'll just put well here, and we don't need a new line at the end of the file. Okay, so here is our test case. Nice and simple. As you can see, the W and the E have their own personal space. There's no overlap between them. If we open this up in some other browser like Firefox or Chrome, you can see that the W extends a little bit outside of its personal space and into the personal space of the E. And that would be thanks to some kind of kerning information in the font file that we are just not handling properly, apparently. And so let's figure out what that is and how we can apply it so that we don't have well looking like WL, which it kind of does now. Anyway, all right, so the first place we're going to look is the inline level iterator in libweb, because that's the thing that breaks inline content into individual chunks that we can then lay out. So I know we call font.width in here somewhere. Yes. So we have a text chunk and we are asking the current font what would be the width of this text chunk. So we can just actually print that out right here. Chunk. I would print out the chunk text, and the width would be whatever that is. So chunk.view and chunk width. All right. And let me just set up a nice build command like that. Oh wait, am I not? Can I not build Ladybird like that? Okay, I don't know why it was like that, but now it lets me. Okay. Yeah, sometimes I get confused by our build system. All right, so we have a well chunk, and this is the width in CSS pixels. So that's our starting point. Now it's becoming too wide, obviously, because the space between these two needs to be snuggled a little bit. So let's follow the trail here. So width of a UTF-8 view in a scaled font calls Unicode view width. All right, and this thing will then iterate over the code points and passing each code point to what exactly? Okay, well here is the, okay, so here we look up kerning for this code point and the last code point, I guess. Right, so we remember the preceding code point, okay. Right. So the way we do this is that we always remember what was the last code point that we looked at. So when we're here, there is no last code point, but when we're here, then the W is the last code point. And then we query the font for a kerning value, which would then be applied to the position of the E. So we would expect to have a negative value here if things are working correctly once we get to the E. So let's log this though. So get kerning value for let's see, sequence. I think we have to do this actually. Last code point, and then we could actually print out what I can print out what we got also, like got kerning value for sequence, something like that. Kerning. All right, sure. Okay, so for W, E, get 0, 0, 0. So we get zeros for everything. So that's not super helpful. Okay, well, so far so good, I guess. Wait, no, that's not so far so good. So let's see what this thing does. So it looks at if the left or right code points are 0, then we just say 0. So that would be the case for this situation here, I guess, when we only have 1 so far. Okay, so then we have a left glyph ID and a right glyph ID. We get those by doing a glyph ID lookup. So we find the glyph ID in the font. Glyph ID is sort of the index, character index inside of the font, and they don't typically map to like Unicode code points, but rather they're just arbitrary IDs within the font file. Not consistent between different fonts or even within different sizes of the same font sometimes. Same typeface, rather. Okay, so we get the glyph IDs for the left and the right. W is the left, E is the right, sure. If either doesn't have a glyph ID, we say there's no kerning, sure. And then we query the font for glyphs horizontal kerning, passing in the left and right glyph ID and the horizontal scale factor of this scale font. Sure. All right, so let's follow that. Okay, so glyphs horizontal kerning. So if there's no kerning table, we return 0. Otherwise, we query the kerning table for glyph kerning between the left and the right glyph ID, and then multiply that by the X scale factor. So the X scale factor is sort of what gives us the font size, because whether your font size is 100px or 10px, we load the same font file. We just apply a different scale factor to it, because it's all vectors anyway. So what goes wrong here then? Okay, so then this does a table lookup, which looks vaguely complicated. Well, not terribly complicated, actually. Just looping through the subtable offsets. And then, let's see, how's this laid out? Current table, OpenType. Take me to the Microsoft Learn resource, please. All right. So what do we have here? The kerning table contains the values that control the inner character spacing for the glyphs in a font. There's currently no system level support for kerning. Sure. Well, I guess the first stupid thing to check is, does the font have a kerning table? So let's just use TTF dump actually, because I know TTF dump can let you look at kerning tables, or it can let you look at all the different tables in a OpenType file. So I think we're picking this up from here, probably display bold TTF. Okay, so the kern feature. Wait, it's not. Okay, so these are the tables, but kern is not one of the tables. So it's a feature. Okay, well, what is mkern then? I'm pretty sure it's supposed to be a table. So I think Jelle was the one who added this originally. Oh, move kern. Okay, so kern. Yeah, Jelle added the kerning table stuff. Which, yeah, it's supposed to be the kerning table. Okay, so the font doesn't have a kerning table. Instead, it has a kern feature. Okay. Kern function adjusts amount of space between glyphs, generally to provide optically consistent spacing between glyphs. Okay. That sounds what I want. Sounds like what I want, but what am I looking at here then? Oh, gpos. Okay. So this is just in a different table. gpos. Okay, so I see. So probably maybe we are using maybe kern is like an older solution. Let's see. OpenType fonts containing CFF outlines are not supported by the kern table and must use the gpos open layout table. Some maybe I'm thinking like maybe the kern is just like some old simple kerning thing, and then gpos is maybe like a more flexible glyph positioning table. Provides precise control over glyph placement for sophisticated text layout and rendering in each script and language system that a font supports. Sweet. All right, so search for kern. Let's see. The only positioning adjustment defined in TrueType is pair kerning, which modifies the horizontal spacing between two glyphs. A typical kerning table lists pairs of glyphs and specifies how much space a text processing client should add or remove between the glyphs to properly display each pair. Let's see. Positioning glyphs with TrueType 1.0. Oh, I see. Yeah. So this sort of talks about TrueType 1.0. And the kern table, I guess, was like, yeah, it was like this simple positioning adjustment defined in TrueType. And then with OpenType, a whole new world opens up, because OpenType fonts allow excellent control and flexibility for positioning a single glyph and for positioning multiple glyphs in relation to one another. Cool. Okay. Okay, so we have gpos in this thing, and script count, feature count. What? Okay, I'm just gonna look at the the struct layouts. Gpos header. Okay, so the gpos header, this thing. So okay, so let's just start parsing the gpos table, and take it from there. So we'll add it to the OpenType tables file here. Gpause. Okay, I mean, even if we don't end up using most of it, it's still useful for the future to just parse more tables and make more of the font data available to the programmer here. So let me go ahead and always on top this so I can see what I'm looking at. We are going to declare a struct gpause header. Okay, so that's the major version, the minor version, and then we have script list offset to script list table. Cool. And then a feature list offset and a lookup list offset. Wow, so many offsets. All right, and then you know what? Let's be like super double good boys here and put a spec link to that as well. Okay, and then I typically do something like this, just for letting you create one of these gpause things. So static from slice read-only bytes, like this. Something like that, and then it just takes a byte slice to keep internally like that. All right, and I guess we can give ourselves a helper to inspect the header. So something like this, header. Slice data. All right, cool. And then, so what do we have here? Scripts, features, and lookup lists. So presumably we have two scripts, default and Latin, maybe? 4 features. CPSP, kern, mark, and mucka. I guess we can look up what those are. So kern, we know, is kerning. CPSP, capital spacing. Globally adjusts interglyph spacing for all capital text. Okay, well, that we're not writing in all capital text right now, so let's not think about that. And then we also had mark positioning. Positions mark glyphs with respect to base glyphs. Cool. Well, let's just ignore that right now. And mucka is mark-to-mark positioning. Again, marks with respects to other marks, required in various non-Latin script like Arabic. Okay, so we are going to zero in on the kern feature today. And maybe we don't have to care about script. Maybe we don't have to care about lookup. Maybe only have to care about this. Let's see how that works. So, what does a feature gpause header? Wait, where was the header again? Oh, here. Okay. Let's see. Okay, so there's a second version of the gpause header actually. If it's version 1.1, then it also has a feature variations offset. Okay, we'll see if we need that. I guess we can start by just printing something as we parse this thing. So first things first, we need to actually just when we're walking the tables in the font file header or whatever, we need to make a note that we found a gpause table. if we do, and if we recognize the tag here. So gpause. I worked on this code somewhat recently. I added these two tables for embedded color bitmaps, which are used in emoji fonts. So it's a little bit fresh in my memory. Okay, so then, yeah, if we have gpause and then we have to pass it to the constructor here, we're just passing in all the different tables. All right. Not now, sea lion. Okay. Okay. Almost there. Optional gpause. Okay. And then I guess when you get asked about kerning information. So let's see, if kern doesn't have value, return 0. So let's instead just say, like, if you have kern, then we check with the kern thing. Otherwise, if mgpause has value, mgpause get glyph kerning. I guess we can just make it symmetrical here for now. We can actually make it completely symmetric. And let's, I was just thinking, should we put this first? I don't know which one should go first, honestly. Well, whatever. We'll leave them in this order for now. I guess I don't know what we're supposed to do if you have both. Maybe one should take precedence or something, but we don't have to figure that out right now. Okay, so let's add this API, get glyph kerning. I feel like this should be allowed to fail though. Like, it would be a better API if it could fail. Also, we don't normally say get. I'm tweaking the API anyway. Okay, yeah, so let's do it this way. Let's check this first, and then if we get a value, kerning.value times x scale, sure. Otherwise, just proceed with the next attempt. Yeah, okay, fine. So I don't want to touch the kern API right now. I'm just going to mess with gpause. Okay, so I guess we can put this at the bottom here, below my aforementioned embedded bitmap routines. So was it I16, gpause, glyph kerning? Yes. Oh, no, optional I16, sorry. Okay, so let's take a look at the header first. Gpause header. I forget what was in there. Oh, major version and minor version. Okay, let's do those first. See what they say. Version. Okay. And then we had, was it features? Feature list offset. Okay, sure. Let's just see what these contain. Okay. You don't like that because line 675. Oh, I can't multiply there, of course. Unused parameters. Well, I'm sorry. Let me just go ahead and void those out temporarily. Okay. So it appears we have gpos header version 1.0, which was this one. And typically in OpenType headers and stuff, version 1.0 is sort of the template for all the subsequent versions. So like 1.1 has the same exact layout as 1.0 plus some additional fields. So they are backwards compatible, typically, at least every instance that I can remember. Okay, so feature list offset is 34, whatever that means. So what are we going to do with this? The gpos table begins with a header that contains a version number for the table. 3 tables: script list, feature list, lookup list. For descriptions of these tables, see the chapter OpenType Layout Common Table Formats. Okay. What was it called again? Feature list. Can I click you? Feature list table. Okay. The headers of the gsub and gpos tables contain offsets to feature list tables that enumerate all the features in a font. Okay. So, offset 34 is presumably the byte offset to this thing. So that's an array of feature record, which is this thing, which is a tag, and an offset to the feature table, which follows on. Okay, so it looks like we're gonna have to do a bunch of binary pointer chasing here. That'll be fun. So we'll start by making a bunch of struct declarations, I guess. And these don't really belong to a specific table. They said common tables, right? Like common table formats. Yeah, so I'll just put them here in the OpenType namespace. So struct feature list. You get to be a basic struct, feature count, and feature record, feature records. And then we need to declare feature record, which has a tag called feature tag and an offset 16 feature offset. Very exciting. Can we get some hyperlinks to those? I guess this is the closest. I'll put that one on both. Okay, so this looks straightforward. You just have a list with this many entries in this array, and then you can walk this array, find feature tags, 4-byte identification tag. Okay, so let's walk that list and make sure that we're understanding this correctly so far. So we have to make a data slice for the feature list slice, which would be mslice dot. So we make a subslice starting at header dot feature list offset. Okay, and then we can read from there. So feature list is bitcast feature list slice dot data. I guess we should check here. Yeah, there's a bunch of bounds checking here missing. I think font is not great about bounds checking in general. Okay, I'm gonna put a fix me about that. Fox me. Make sure everything is bounds checked appropriately. But yeah, if feature list slice size is less than size of a feature list, well, then we're going to have a problem. Okay. And let's see. This will give us the length of the array. So now we can read that out from feature count. Let me actually make this a little bit larger. Feature count. Okay, here we go. Feature list table, feature count. Can I get rid of the... I just wanted to get rid of the table of contents on the left side there. Okay, this is better. So let's read out the feature count. For size ti feature list dot feature count. Okay, so then we can look at the feature records, which let's just do this for now. Feature record. Okay. So it had a tag and some kind of offset, right? Feature record dot tag and offset. Okay, let's just see what they say. Right, the tags are going to be 4-byte strings, I think. So we can probably just do something like this, just to take a look at it. No, not quite. What if I did that? Ah. Okay. Hey, look at them. So we got our feature records here. We have CPSP, kern, mark, and mucka mucka. Right, so kern is the one that we're looking for. So from this table, what we really want to do is we want to extract the kern feature offset. I'm just thinking here, we need to avoid nesting, I guess. So we need to find the kern feature offset. That gives us the offset to the feature table from the beginning of feature list. Okay, so let's do something like this. Optional offset 16 kern feature offset. If feature record feature tag from string kern, then kern feature offset is feature record offset. I think once we find that, we can actually break. And if we don't find it, that means that we can bail out. So return. I should probably log something in these failure cases. No kern feature found in gpos table. All right, and here, gpos table feature list slice is too small or something. I don't know. Okay, so once we have the kern feature offset, that's an offset to a feature table, So a feature table defines a feature with one or more lookups. The client uses the lookups to substitute or position glyphs. So we wanted position glyphs, right? So we're not within gsub. We are within gpos. Sure, blah, blah, blah. Can't we just parse it? Feature table. Yeah, I'm not going to read all that right now. I may have to go back and read it if things don't pan out. But for now, let's just add more. Make more structure declarations. So feature, I guess we can just call it feature. This is going to have an offset 16, feature params offset, and a lookup index count, and a lookup list indices array. All right. And can I get a permalink to you? Yes, I can. Okay, so the feature table has a number of lookup list indices for this feature, and then an array of those things. And it has a feature params offset. Offset from start of feature table to the feature params table. Feature params table. Was that the optional thing? No, that was variations. That's maybe not the same. I was thinking what was in GPOS header version 1.1 had an additional offset, but that was variations, not params. So maybe params will be relevant for us. We'll see. So let's make a slice for the feature table. So that would be a feature slice, first of all. And these offsets are typically not from the start of the file, but rather from like the start of the table that refers to them. So we have to figure out where was that offset from. Feature list offset was from the beginning of GPOS table. And then the feature record, no, what was it called? Feature record offsets from beginning of feature list. Right, so it's part of the feature list slice. So it's a subslice of that with an additional offset. So we take the kern feature offset, and then again, ignoring the bounds checks for now and just powering forward. So feature is bitcast feature slice.data. All right. Okay, so assuming that we have one of these things, then we can print out the feature params offset. Feature params offset is and we also had the lookup index count. And then we had an array of those things. So let's see. 3 spaces. Okay, so let's print these out also. Lookup list indices of I. All right. Oops. I just want to see some output. Okay, well, very exciting. There's one lookup index. So that's good, I guess. Lookup index count. So I wonder if we need to handle multiple lookup indexes. Let's assume that we do, and maybe write the rest of this function in a loop around this. Lookup list table. All right, so the headers of the gsub and gpos tables contain offsets to lookup list tables for substitution and positioning. Okay, the lookup list table contains an array of offsets to lookup tables. Lookup offsets. Wait. This was in the header. Okay, so there's a lookup list that I need to look up. Offset to lookup list table. So it seems like we're gonna have to declare this thing as well. So lookup list. I thought maybe we only needed the feature stuff, but it seems like features refer to lookups, whatever that means. All right, so lookup list doesn't look so difficult. Just a big endian U16 lookup count and an offset 16 lookup offsets array. Okay, well, we've seen these before. So, oh, I guess we should have made the lookup thingy. I mean, we can make it now, actually. So, lookup list slice, or it's the same as the feature list slice. So let's make that up here also. The same style, because they're both offsets in the header. Lookup list offset. If it's smaller than the size of a lookup list. Again, I know that we are missing some of the bounds checks that we're gonna need here. We're gonna need to check all the slices eventually, but right now we are not doing that. Not offset, slice, my bad. Okay, so now we have a lookup list slice, and that should allow us to make a lookup list reference just like this. Okay, lookup list slice data. So we needed that down here because we have indexes into the lookup list. So what is in the lookup list table? It is a lookup. Is that what it's called? A lookup. All right, I guess we should declare that also, a lookup. So more cool things. Lookup type, lookup flag, subtable count, subtable offsets. By the way, with the word subtable, this is a little bit of a pet peeve of mine, but subtable, they're inconsistent in OpenType, the OpenType specs about how they capitalize the T. So sometimes it's subtable with a capital T, sometimes without a capital T. And this is very frustrating. So I decided I'm just sticking with subtable as one word because it is one word in the dictionary. So ignoring the mixture of capital and lowercase t's. Offsets, that's an array. And ooh, that's awkward. There's a U16 after the array. This field is only present if the use mark filtering set lookup flag is set. Well, we're not messing with marks right now. Maybe I can just ignore that for now. Okay, but I did want a permalink, so let's get one of those. Having these links is amazingly valuable when you come back later to this code and you try to figure out what something is, because then you can click the link. It takes you right to the explanation of the data structure. And certainly for other people who are not familiar with the code, I'm hoping that it will be helpful for them. So now we have declared what a lookup is. So I guess we can make a lookup slice. So that would be a slice presumably into the lookup table. No, wait, hold on. Array of offsets to lookup tables from beginning of lookup list. Okay, so we start from the lookup list slice, and then we use the feature dot lookup list indices I. Okay. And then now we are looking at a lookup. So what do we have in there? Types, flags, subtable counts, and other gunk. Lookup. Let's just log it. We'll see what's in there. Oops. Lookup type. Different enumerations for gsub and gpos. Okay, I don't know what that means, but we will learn it eventually, I'm sure. Flag, subtable count. And subtable offsets. Okay, well, let's print these out so far, see what we're looking at. Lookup. Wait, what? Lookup list? Did I not do anything with lookup list? Wait, what was in the lookup list? I already forgot. Lookup offsets. Oh, I'm probably doing something wrong now. Or maybe I'm not. Because I had a direct index into it. So I don't need necessarily to walk it. Okay, let's just mark this as maybe unused for now. And then we'll see what happens. Okay, so lookup. Lookup type, lookup flag, subtable count. These are pretty large numbers. Do they make sense? I guess we can compare to TTF dump. So let's see. Gpos. So we're looking at the kern feature, lookup list index 1. Wait, lookup count 1. Lookup index count 1. Let's see. Are these the lookup tables? Lookup index count. Let's see. Let's print it out here, actually. Lookup index. Okay, just so we can see what lookup index we're actually looking at. Lookup index 1. I think that's that one, right? Yeah, lookup list index 0, 1, 2, 3. So 1 here. And that would be, so this is the lookup list. So this is lookup list 0. So we want to look at number 1, I guess, here. The pair adjustment list. Sounds good. Because we want to adjust a pair of glyphs. So we have lookup type 2, lookup flag 8, subtable count 2, none of which match what we are looking at here, because the numbers we got were very large, which is always suspicious. So lookup list slice. Oh, wait, I'm using the index to... Wait, what am I doing? Lookup slice. I should be using an offset of some type here. Lookup. Oh, I guess I have to get that from the lookup list. This is where the offset comes into play, the maybe unused thing. Okay, here we go. So now it's no longer maybe unused. And let's see if that works. All right, we got small numbers. Type 2, flag 8, subtable 2. Okay, we're good, we're good. We are looking at the same stuff as TTF dump. So now I guess we have a bunch of pair adjustments here coming to us. Presumably these are X advance adjustments. Yeah, so this is definitely the type of information we're looking for. We want to modify the X advance, which is like the horizontal positioning of the second glyph in the pair, I guess. Yeah, so this information looks like what we're after. So let's see. So now that we can iterate through these, what do we have exactly? We have a lookup, which has a subtable count, and we had 2 subtables. So I guess we need to actually look at those subtables. So what is a subtable in this context? Subtable. Each lookup type is defined with one or more subtable formats applicable to the given lookup type. So let's look here. Subtable. Okay, so there are a couple of different types of subtables. There's pair adjustment positioning. So those are the ones that we're interested in, I think. Pair adjustment positioning subtable pair pause is used to adjust the placement or advances of 2 glyphs in relation to one another. Yes. For kerning data. Yes. Okay. So blah, 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 blah. Pair pause format 1. So there's format 1. Is there a format 2? Class pair adjustment. And we had 2 subtables. Okay. So I guess we should check what's the difference between these. So pair pause format 1, or maybe TTF dump can just tell us what it has. And let's see what it said. Pair adjustment list, lookup format 1. And we have a second subtable. Okay, so after a lot of information, lookup format 1, single adjustment, pair adjustment. Okay, so how do I get to the next subtable? Coverage. Okay, so maybe there's no coverage. How do I get to the next one? Easily. I guess I just have to... Oh, shoot. I don't have a complete output. Okay, now we have the complete output. Pair adjustment. Okay, so we have pair adjustment list and pair adjustment class. Then mark to base attachment. So I guess this is the mark or whatever mark thing. Single adjustment value. That might be the all caps stuff. Let's ignore those. So I think, so we have two types of subtables. Two subtables for pair adjustment. One called list and one called class. And they both have information. Cool. So question is, which one do we need? Maybe we just have to implement both. Let's see. Pair pause subtables can be either of two formats. One that identifies glyphs individually by index and one that identifies glyphs by class. Oh, interesting. So I guess the second format is like, if maybe you can like group up glyphs and say like, oh, if a class A glyph is next to a class B glyph, then you adjust the class B glyph by minus 50 design units or whatever. That would make sense because you're gonna have a lot of glyphs that are kind of similar to each other, right? Like we're using the text well, but you might, I would imagine that if you say well or wall or vocal or like any combination of these, I would assume all of these get the same kerning applied. Right. So question is if the font is like smart enough to know that. I guess that depends on the software used to make the font file. Anyways, we're just gonna have to investigate. So let's go with the assumption that that's how it works, and also the assumption that this font file was generated in that way. And then if it turns out that I misunderstood it, we can always backtrack. So let's see, let's start with the second subtable. We have to implement all the subtables, obviously, because I think it's just a compression technique, because you might have the same exact kerning for like 30 different pairs. And then you have some specific one that's totally unique. And then that goes in the first list. And the non-unique ones go in the second list. Okay, so let's loop over the list of subtables here. J, look up subtable count. And the subtables offsets are relative to what? To the lookup list? Or I forgot where they were. The lookup list table. Offsets to lookup tables from beginning of lookup list. Yes. And then subtable offsets. Lookup subtables are from the beginning of lookup table. So, okay, so from the lookup slice. Subtable offsets J. Okay, so then this would then be a, what on earth was it called? A pair pause format. Pair pause format 2. That's the one. Right. So let's see. Format identifier. Okay, so the first, there's a U16. I bet you that both of them start with a U16 with the format identifier. Yeah, so that's how we know what type it is. So we could actually make a pair pause format is a big endian U16 where do I want to go? I want to go to subtable slice dot data. Okay, so pair pause format. Okay, and then if pair pause format is 1, fix me, implement pair pause format 1. Ignoring, or yeah, no, this can just say that actually. Okay. And then here, let's say that we get one of these. So we bitcast to a pair pause, gpause, pair pause format 2. Subtable slice, and then we have to declare that. At least this one is gpause specific, right? Because it's part of the gpause file. Right, so this is not a common thing. Okay, so we have, again, a little table to declare. So struct pair pause format. Oh, that's the wrong one. This one is the one that I was trying to make. Pause format. Coverage offset. Value format 1, 2. Class def1 offset. Okay. Class 1 count. Oops. Class 2 count, and then class 1 records. Array of class 1 record. Ooh, which is an array of class 2 record? What's a class 2 record? Oh. Well, I can't declare that up front because I don't know. I don't have the counts at compile time. Cool. So we're just going to have to do some offset math for that stuff. But let's get a permalink for this fella. All right. And we should be good to take a closer look at this thing. Data. Okay, so pair pause format 2. I forget what was in it. I guess the format. What else was in there? Class 1 count. Value formats. Okay, I guess let's just log these, see what they are. Sure, well, whatever. Let's... All right. So pair path format 1, implement. Oh, did we never get to the 2? We only had pair path format 1? Oh, wait, no, I'm bailing on. Wait. Pair path format, I'm never printing that. Okay, so am I not looking in the right place maybe? Because the DTF dump had lookup format 1 and 2. And we had 2 subtables, so subtable. Oh, wait. I shouldn't return here. I should just continue the loop. That's why. That's why it's falling apart. Okay, pair pause format 2. Cool. So what did we have in that thing? We have value format 40, 1 of 487. Small numbers, possibly correct. So what did they say? To coverage, range count. Okay. Value format 40. 40, that looks good. Class def. Okay, don't know what those are yet. Class def, they said. Class def. Class def offset. Offset to class def table. Class def. What is a class def? Is that a common table maybe? Class definition table. That sounds like what we're interested in. Okay, so what does that do? In OpenType layout, index values identify glyphs. For efficiency and ease of representation, a font developer can group glyph indices to form glyph classes. Ooh, this sounds like exactly what I was talking about. Class assignments vary in meaning from one lookup subtable to another. Sure. Blah, 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 blah. The class def table can have either of 2 formats, one that assigns a range of consecutive glyph indices to different classes, or one that puts groups of consecutive glyphs indices into the same class. What? Okay, so there are 2 formats. Let's just see which one. See, class def 1. So wait, there were 2 class defs, right? Class def 1 and class def 2. Class def 1 upset. So I guess these are sort of the left glyph and the right glyph for the first glyph of the pair, right? And the second glyph of the pair. Okay. So is it a class def format 1 or class def format 2? Class def 1, class range count 381. It doesn't say what the format is. But it does say class range count, which is only present in the second format. So let's hope that this is the one that they're using. Otherwise, we will have to bail with a fix me. So, oh wait, no, this was a common table once again. So what was in that thing? 2 U16s and then a class range record. Sure. Class format and then class range count. And then an array of class range record, which is one of these things. 3 U16s. Riveting struct. All right. big endian, use 16. And then you have to be something like that because class is a keyword, obviously. Okay. And let's also get some of them permalinks up in here. All right. Then, what is one of these things then? We have class range count. Okay, so then you have ranges with the start glyph and end glyph, and then apply to all glyphs in the range. Oh, okay. So I guess we'd look for the class range record, the left side glyph and the right side glyph. We look for one where it's in that range, and then we know that that is the class of that glyph. So let's see. This feels like a lambda because we got to do it twice. So let's see, get class. Okay, so what is it that I want to do exactly? I want to offset to class def table from beginning of pair pause subtable. So I need the offset and the glyph ID. So I have the glyph ID and I have an offset 16 glyph def offset. And I'm going to give you back either, what was it? Yeah, so I'm going to give you back the class, or optional, if I don't have a class for this, I will not give you a class for it. Okay, so class def, what was it called? Class def format 2. Class def format slice is relative to the pair pause. Okay, so pair pause, we're calling that subtable slice. Okay. Glyph def offset, sure. Class def format. We should really look at what the format is actually. Def format is 1, then that's a fix me. Okay. Yeah, there are more checks that need to be here, but right now we're just trying to get to the information that we need wherever it is. It feels like we're just going through a long labyrinth here. Offset to class def table. Okay, so the class def table, we're gonna get there. Let's see, before the brain rot sets in. So class def format 2, class def format slice, datum. What can we get from you now? We can get the format and the range records. So I wanted to loop over those, right? Range count. And then if glyph ID is within the range, so class def format 2 dot range records I. Oh, I didn't format those nicely. Okay. So So it needs to be there, and it needs to be below or equal to the end glyph ID. If it is, then that's the thing that we found, the thing that we were looking for. So we should return the class. Right. So class def format 2. I guess we can call this like range. Make this a little nicer here. Range. Class, there we go. Okay, so if we find it, and this could probably be replaced with a binary search, but let's just ignore that for now. Okay, so now we have a function that returns the class for a glyph. So let's say left glyph class, or just left class maybe. Get class left glyph ID and the class def1 table offset. Who had that? Who had class def1? Pair pos format 2, of course. Class def1 offset. All right, and for the right class, we get there. Okay, and then if we don't have both, has hello. If not, if either one doesn't have a value, that's a, I mean, that's actually just missing, but for now, let's log here. The glyph class for need a glyph class for both sides. I don't know, something just so that I can know what happened. And I guess I should print something out. Classes. Left class and right class. Okay, so what do I do with these? Let's see if we get something reasonable looking. Need glyph class for both sides. All right, so didn't quite work out. Okay, so what are we doing? Pair pos format 1, sure, yeah, whatever. So let's see if we're looking at the right thing. I should probably dump out some information in class def format 2. Class format. Range count. And then it would be good if I would do these so that we get something. Gotta put the Okay, so class format 2, class range count 381. Class 381, that's at least that's the same range count that we had here. Okay, and then the ranges look like this. So that's like start glyph, end glyph, class value. And are we messing this up somehow? Return range class. Found class for glyph. And then here, like, no class found for glyph. Just to see if I am totally screwing this up somehow. No class found for glyph 732. Wait, are we passing that for both? Oh, wait, back up. Oh, this is the word well. I was just thinking, like, why would it try the same glyph on the left and right side? But it ends in LL, right? Well, LL. So that would be L and L. We need to be looking earlier. So we need to look for classes. Oh, check it out. Okay, so it does find classes. Okay, so here we can actually see them. This is the WE. This should be the WE lookup. Chunk well. Get kerning value for sequence. Hello. So 459 and 615. I think those are the W and the E. So 459 on the left side would be, assuming this is the left side table, class def 1. 459, class value 44. That's right. And then the second table, glyph ID 615, class def 2. So 615 would be in this range here, class value 2. And that's good. So what do we do with these? Let's see, a class 2 record has 2 value records. So we want to get to these, positioning for first glyph and positioning for second glyph. Okay. What is a value record? Value record. Are you in the common thing? Value record. Value records. Where are these declared? Oh, here. Value record. Blah, 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 blah. What is this? GPOS subtables use value records to describe all the variables and values used to adjust the position of a glyph or set of glyphs. A value record may define any combination of X and Y values in design units to add to or subtract from the placement and advanced values provided in the font. Note that all fields of a value record are optional. To save space, only the fields that are required need to be included in a given instance. Because the GPOS table uses value records for many purposes, the sizes and contents of a value record may vary from subtable to subtable. A value record is always accompanied by a value format flags field that specifies which of the value records fields is present. Okay. So it's one of those where we can't just make a struct declaration, but we have to look at the flags in the value format or whatever it was called. Value format. Yeah. So these, I guess, are some kind of a bit mask that tell us which of these fields are present. Value format flags. This sounds, I've seen this in other OpenType tables as a similar pattern. So I guess we can make an enum for this. So let's see. Is this part of GPOS? Yes, it is. So I guess you get to go in here. Value format. Looks like a U16. Okay, so X placement. Cool. Y placement, and then we have advance. What am I doing? And then we had placement device and advanced device. Okay, so let's do a little multi-cursor business here. Ha. And reserved, which probably don't need to declare. Okay, so let's see. Pair adjustment positioning. Class pairs. Wait, so how do we, can we verify before we proceed here? So we had 44 and 2. And here is presumably where you actually find the pairings. So can we look for 44? (44) and 2 would apply a minus 120 design units on the right-hand side glyph. Sounds plausible that that would solve the problem. So it would be a 120 design unit, which we would of course then scale to get the actual pixel count. I can believe it. Okay, so how do we index into that thing? Because it gets real messy because we have to look at the value format 1 and value format 2 to know which type of information is present. And in our case, is value format 1 or value format 2? What does that mean? Value format 1, value record definition for the first glyph of the pair. Okay. So what does that mean? Value format 1. Value format 1 applies to the value records for the first glyph in each pair. The single value format field applies to value records for all first glyphs. If value format is set to 0, then the value records for the first glyph will be empty, and therefore the first glyph is not repositioned. Value format 2 applies to the value records for the second glyph. The single value format field applies to value records for all second glyphs. Okay. And we had the same as they did, right? What's it called? Pair adjustment class. Value format 1, 4, and 0. Okay. Class values, blah, blah, blah. Okay, we'll see how this goes. So I want to figure out how large is each entry in this array, which is one of, Yeah, every entry is one of these. So it's like a packed array. So we have to do the array math. I guess we can use pop count, actually. If we just look at the... Because each of these, if we look at the value format, what was it called? X advanced or whatever. They were all 16-bit, right? Yeah, they're all 16-bit values. So we can take the number of bits in the value format, multiply that by the size of a 16-bit value. So multiply it by 2 bytes per 16-bit. And then that gives us the size of one entry. So like value 1 size. Do we have pop count? Pop count of the value format 1. Who had the value format 1? It was in the pair pause format 2. Okay. So the pair pause format 2. And only the bottom bits, thank you. Do I have to cast that to like a U32 or something? Yes, okay. Okay, and then, man, this is gonna get pretty gross, but then we can figure out offset math and geometry math. Not my best friends, but we're gonna get through this. So class, this is a class 1 record. So class 1 record size is class 2 count times, oh, class 2 record is both values. Okay, so we need to add both value sizes together. We'll call that a value pair size. Okay, so class 1 record, or I guess we could call it the class 2 record size, actually. That's getting a little messy here. So class 1 record size is class 2 record size multiplied by pair pause format 2 class 2 count. All right, and then we can index into this thing. So the item index is going to be, well, the item offset is going to be class 1 record size times left class plus the right class times class 2 record size. Does that make sense? Item offset, let's see if that works. See if we get something plausible sounding. Hmm. 3830, okay. Well, and then we need to read from there. Ah, man, I wish I could declare this somehow, but no can do. So it's here. This here is the thing I want to look at. So at the end of the pair pause format 2 table, we'll call it the item slice, is the pair pause or the subtable slice dot slice, and then size of pair pause format 2 plus item offset. Could this work? And then based on the presence of the flags in the value formats, so let's see, if pair pause value format 1 and value format, so we have to do them in order now. X placement comes first, my bad, almost messed that up. Yeah, X placement first. All right. Okay, so if that's a match, then we read out, I want to read out a U16. So let's make a memory stream, fixed memory stream thing over item slice. Okay. So stream.read value big endian. I hope this works. Okay, so can I just make these maybe? Why advance? Why even advance? I think those are all the values, right? Yes. Okay, so maybe what we should really do is call this a value record. And we can make a thing that gives you these in memory. So let's see. Auto read value record. Value format gives you back a value record. Okay. And then we do this value record. Okay. Does that not work? Oh, right, yeah, of course, I have to say X advance or X placement. And that's a fix me right there, fine. Okay, so let's read out the various values. It'll be a little bit awkward. I think it's generally sound. Okay. And okay. Then we do this twice. Pair pause format 2 dot value format 1. Okay, now I have the two value records. And I'm just going to find out what's in them. which will be we were looking for the X. What was in the TTF dump? I was here somewhere. X advance. Right, we're looking for the X advance. All of these are value 1. It's kind of interesting. I guess I would have expected it to be... I was going to say I would expect it to be value 2, but that doesn't make sense. Because we're changing the advance of the first glyph. We're not moving the second glyph, we're changing the advance of the first one. Makes sense. Okay. At first I thought it didn't make sense because we should be moving the E closer to the W, but really we're just making the W shorter, making the advance shorter. So here, the result that we would want to return here, because of the way this function is used. So right now, the way that this is called, like our API doesn't allow us to do anything fancy. It really just controls the advance, right? Where was that Unicode code? Unicode view width. Let's see, width plus equals kerning. Yeah, so it's really just controlling the advance, or controlling the width by doing that. Wait, how is it used when we paint then? How do we use this when we paint? Painter. Point. So point is where we are painting. And if we get a non-zero kerning value, then we translate by this when we receive that. Okay, so when we so we need to return. We're gonna have to make this smarter to be able to handle more fancy things. But if all that you're doing is changing the advance of the first one, I think we can just keep the API that we've had. It should support this one specific thing, if I'm thinking about it correctly. So basically, it would be like value record 1 dot x advance. Let's see. So it's supposed to be minus 100 something, right? X advance. Well, it would be a miracle if I actually did that correctly with everything there. Let's see. Item offset X advanced 24. Okay, so I made it worse. Great. So now I'm shifting it a little bit to the right. Okay, so I did not do the math right, probably, for the item offset. Okay. So let's double check our math here. So value sizes, value 1 size, value 2 size. Okay. Just double checking those, and then class 2. I mean, we know the class 2 record size. Let's print it anyway. Class 1 record size. So class 1 record size. Okay, so there's 1 byte per class 2 record. I did get that right, didn't I? Class 2 record. There's one value record per side. Sure, yeah, and one of them is empty. So we only have the one entry in this one. Oh, but it should be the size of U16. We forgot about that part. Because it's an odd number, so that doesn't make sense. Ooh, look at that. That looks like it might be correct. 44.2, returning X advanced, 65.416. Okay, so I was probably supposed to make these I16s, not U16s. So let's fix that real quick. But it doesn't matter because it still gets returned as a U16. It just looks goofy in the output. Oh man, that actually looks good. Man, that was took a moment to get there. Let's see. Let me get GIMP here and we can compare. Put them one on top of the other. Okay, and then do a little bit of that, a little bit of this, and we just see how we are doing here. Okay, well, we are not exactly the same. In fact, we're quite different. That's surprising. It doesn't even look like the same. Is that the same typeface? Enter display bold. I wonder if this if Chromium is picking up enter bold. How can I check that? Maybe I can, because I know enter comes with like bold and display bold. Let me see what we can do. So base res fonts. Yeah, I only have the display ones here. What if I didn't have any of these and instead I have those here. I guess what if I only had enter bold? Let's see. Is that closer to? So this is Ladybird. Oh yeah. That's much closer. Okay. Oh man, that would have driven me bananas, but it was not the same typeface. Oh, thank goodness. Okay, so I think when I put the enter fonts into my Serenity directory, then I only put the ones called like display. I guess because I thought, oh, these are suitable for display. I don't know, but I only put those. And maybe Chromium didn't pick those up, and it seems like it didn't. So it's still not exactly the same. Our anti-aliasing is different, positioning is a little different, but still, the kerning is definitely better than where we started. All right, so yeah, you can see now that the E is in the personal space of the W. And probably we need to change the way selection widths are calculated, because right now, I think we calculate the selection width by like making a substring slice. So we do a W only, and then we measure that. And because you're measuring it by itself and without the E next to it, it's going to get a wider width. But then when you put the E there, the W gets smaller. So we need to figure out how to communicate that information. But this is good enough for me for today, for sure. Like, now we just need to clean up all the mess that we made here, because we got a lot of debug statements. And you know what? I'm gonna do this. gpause debug. Can we do something like this maybe? So that if you want this, you can actually turn it on for yourself. Because I'm probably going to be poking at this soon again, I can imagine. And what on earth? Well, he got upset. Let me just check real quick if I do this. gpause debug. Okay, oh, and all of that stuff was outside actually. So wait, what did I want to do? Git checkout. Everything I did in libweb, for example, that was just debug logging. Yes. Debug logging, debug logging. That's not all of it. So I think, I mean, I'm happy with this for the video because we got the W and the E to snuggle up together. And that is what I set out to do. But it sounds like now we only care about the classes of glyphs getting kerned together. So we should also do that. The other table that had like unique pairings that were not part of classes. And then it sounds like we need to make the API for this a bit more sophisticated so that we could handle, like if you have a font that says, oh, you should move both the left and the right hand side glyphs in this or that way when they are paired together. Because right now, like with our API that just returns a single integer value, it can only tell you like whether to essentially like go further apart or closer together. That's all it can do. So we need to improve our API to be able to take advantage of more information. But thankfully, in this case, the information was simple enough that we don't need to change the API. But, you know, we should obviously deal with that also so that we can support more sophisticated fonts. Oh, my goodness. Okay, so this has been a journey. Still relatively painless, other than a handful of small mistakes and misunderstandings. And I'm sure I screwed at least one thing up somewhere, but still, it's not bad. So, let's see. Let's see if we can, if I still have the the file, by the way, from the original tweet. I should have it. It should be in my here. So this is what I was screenshotting. And if we compare that, let's just see. Hello. Where are you? Not right now. Here. Okay, so I probably had a bit of a zoom going on. Oh, wait, now I don't have the display bold anymore. But yeah, we can see that the WE, shut it. The WE have been brought together at least. Still feels like still needs work, I feel like. But those are good. The N and the D are pulled together a little bit, are they? Not sure. I guess we could print out which pairs get kerned. We could print that. Where was that? Scaled font? Code view width. If kerning is not 0, pair. Kern. That would be interesting to see what that says. Just out of curiosity here. And let me bring back all the display fonts so it's the same way it was set up before. Okay, so WE, FR, and RI are the ones that get adjusted. And FR are pushed further apart. Same with RI. Interesting. Okay. And we're just doing what the font says. So that's cool. That is cool. And it would be nice to see it exactly at the same size. Why did I zoom before taking the picture? That's annoying. Let's see, paste. Double checky check. No, that's not the same size, bruh. Is that the same size, bruh? Nope. Nope, nope, nope. Okay, well, I don't know why I'm making this so difficult. Cool. That looks kind of interesting. So the E comes closer here. Everything shifts to the left in the beginning, but then it's counterbalanced towards the end by the FR and the RI pushing the text or pushing towards the other direction. I didn't think the FR and the RI looked so bad here. Anyways, we're just going to do what the font says. So I think that's fine. I am happy with this result, at least. I think that's great. And that was a satisfying little journey, even though it was a bit tiresome at times. So let's make a commit out of this stuff so that we don't lose it. Okay, git add. Okay. What do you not like? What failed exactly? Fail. Check debug flags. Oh, shoot. It's because I added that thing, the gpause debug. That's a bit annoying. So they want me to put that in debug.h.in, which causes a huge rebuild. I guess I'll put it here. Let's see. Alphabetical order. I'm thinking O for OpenType. I'm an OP. Where is it? Here. If and def. OpenType gpause debug. Okay. Yeah, and that's a massive rebuild, of course. Although, okay, wait, it didn't turn out so bad. No, you still don't like it? What don't you like now? Oh, because I didn't include it. Okay. Can I do this correctly? Now Clang format doesn't like it? Okay, well, I screwed something up there, that's for sure. What on earth? What do you not like? Oh, it needs to be in all the debug macros. All right. There's so much busy work when you add a debug flag that I never remember all the debug macros. It has to be added to this file. Gpause debug. Can I please be allowed to commit this? Yes, finally. OpenType. Add some initial support for kerning for glyph positioning with gpause, or for kerning glyph positioning. This patch parses enough of gpause to be able to gpause table to be able to support the kerning information embedded in inter. Need to, yeah. Since that specific font only applies positioning offsets to the first glyph in each pair, I was able to get away with not changing our API once we start adding support for more sophisticated positioning, we'll need to be able to communicate more than a simple kerning offset to the clients of this code. Yeah. That was okay. It's okay. Could definitely be better. Let's see. Wonder how far away a full rebuild of Serenity is. So we could see that it works there. It's not that much to rebuild, maybe? Not much at all? Okay. I thought maybe it would be a 5-minute rebuild, which would be a bit tedious to wait for, but looks okay. And what if I decide to use enter as my system font? Oh, then we get to see all of these. That's cool though. So now we see that it actually applies those. Enter, display, bold. Click. Wow, look at all those little kernlings. That's delightful. So now if, say I had a file or a directory called well, then presumably that would be nicely kerned. Yeah, see, it's kerning it by 0.677 pixels. Very cute. And we will actually reflect that in the rendering because I'm not sure if I can actually see it here, but we do split pixels into 3 subpixels, or into 9 subpixels actually, both vertically and horizontally. So this, even though the adjustment is less than a pixel, you will still see it in the result. So that is awesome. Okay. I am a little tired, a little warm, so time to wrap it up. But this was nice. I'm glad that we could make it happen. So this will be the end of the video. If you made it this far, then thank you for watching, for hanging out. I hope that you saw something interesting today, and I'm certainly very pleased with the result. But as I mentioned repeatedly, we also noticed that there's a lot more information in this font that we are not making use of. And our API is not even smart enough right now to be able to make use of it, even if we started parsing out the information. So there's work to do, but this is fantastic. And I'm going to show it to Rasmus, obviously. Hopefully he will appreciate the slightly nicer looking well. Anyways, thanks for hanging out. See you all next time. Bye.